Good day, viewers. My name is Dr. Chris Esekaibe. It's nice having you today again in another class. Today we shall be looking at a vital topic in numerical analysis, and that topic is the method of false position. The method of false position. We want to see how we can use this method to solve algebraic equations in numerical analysis. The method of false position is one of the oldest methods, if not the oldest method, for finding the real root of an algebraic equation. Remember, the equation is of this form: f of x is equal to 0, and the equation is non-linear. It can be a quadratic equation, a cubic equation, a quartic or quintic equation, or a polynomial of any degree. The essence of using a numerical method is to find a real root. In our previous classes, we used the bisection method, and in our last class, we used the Newton-Raphson method to solve the same problem. And we saw how the Newton-Raphson method converged at the 5th iteration. Even at the 10th iteration, the bisection method was not able to converge. It was only able to achieve accuracy at 2 decimal places. Now we shall be first of all examining the method of false position, see how the formula can be derived, and again we shall also use this same formula, which is the method of false position, to solve that same problem: f of s equals x raised to the power 3 plus 2x minus 1 equals to 0. By the time we do that, we'll be able to compare the results with the results gotten from the bisection method and the Newton-Raphson method. Once again, my name is Dr. Chris Esekaibe. This YouTube channel is Dr. Chris Esekaibe. Please subscribe to my channel. Click on the bell button for notifications. Share my YouTube videos on your social media platforms. Like my videos. Be part of those that are sharing knowledge across the globe. Now, the method of false position. This method of false position closely resembles the bisection method. It closely resembles the bisection method. It closely resembles the bisection method. So, you know the bisection method, that means we are going to look for two values. In this method, we choose two values. Two values, x0 and x1 and s subscript 1, such that f of x0 and f of x1 are opposite in signs. That is what we do. So we choose x0 and f of x0 to ensure that f of x0 and f of x1 are opposite in signs. That means they are of opposite signs. Since the graph y is equal to f of x, it crosses through the x-axis through x, crosses x through the x-axis on these 2 points, on x0 and x1. So the graph crosses through the x-axis between the 2 points, x0 and x1. Then this means that there must be a root between x1. Then a root lies between x0 and x1. So when this graph crosses the x-axis on the 2 points x0 and x1, it means that a root lies between the point x0 and x1. So the equation of the chord joining the points, these are the points x0, f of x0, and another point x1, f of x1. So the equation of the chord joining these 2 points, the equation of the chord joining the 2 points is given as, that means the equation of the chord joining these 2 points will now be y minus f of x0 all over x1 minus x0 is now equal to f of x1 minus f of x0 all over x1 minus x0. So this will now be the equation of the chord that is joining these 2 points, x0 and f of x0 and x1 and f of x1. Then if we have this bisection method consists of replacing the part of the means of the chord joining the points and taking the point of intersection of the chord with the x-axis as an approximation of the root. This point of intersection is given by putting y, putting y is equal to 0. So this is achieved by putting y is equal to 0. When we put y to be equal to 0, what now become of this particular equation here? What become of this? When y is put to be 0, we are now going to have minus f of x0, because y here is 0, all over x1 minus x0 equals f of x1 minus f of x0 all over x1 minus x0. Now we are going to cross multiply. Then this will now give us, this will go here, x1 minus x0 into f of x1 minus f of x0 is now equal to minus f of x0 into x1 minus x0. So doing this, it then means that we are now going to have our x1 minus x0 will now be equal to minus f of x0 into x1 minus x0 all over f of x1 minus f of x0. So now, making x1 the subject of the formula, x1 will now be equal to this x0 will cross to the other side, x0 minus f of x0 all over f of x1 minus f of x naught. Then you now have x1 minus x naught. Now you can see that x1 formula is having x1 in between. So this simply means that the second approximation to the root of f of x equal to 0, the second approximation will now be x2 will now be equal to x naught minus f of x naught all over f of x1 minus f of x naught. Then this now have bracket x1 minus x naught. So this will now be the method or the formula that is used in this method of false position. Now you will know why it is called false position. Every other, just like the bisection method, we shall be looking at two values. Here we choose two values, x0 and x1, such that f of x0 and f of x1 are opposite in signs. For the bisection method, we bisect at each point, but here we will choose x0 and x1. Then we'll now use this formula to get x2. We'll be using this formula to get successive iterations. The steps again are iterative steps. So that is how the formula is going to work. So it means that, permit me to rub up the board. This is how the method of false position. Now this is how the formula is derived. This is how the formula is derived. Permit me to write the formula at the top right hand of the board. Here our x2 is equal to x0 minus f of x0 all over f of x1 minus f of x0 into x1 minus x0. So this is the formula for the method of false position. It is as simple as that. This is the formula that we are going to be using. So you can see how the formula was easily and cheaply derived. That is how the formula was easily and cheaply derived. Now we are going to pick that same example we solved using the bisection method and the Newton-Raphson method. And that example is f of x is equal to x raised to the power 3 plus 2x minus 1 is equal to 0. Solve, we have to solve using or find a root using the method of false position. So we are going to find a root using the method of false position. That method or this method of false position is given or is gotten or is the formula above has to do with the method of false position. So we are talking about false position. That is the formula you are to use. Now let us look at the solution. The first thing we need to choose our 2 points x0 and x1 such that f of x0 and f of x1 are opposite in signs. Now let's start from s is equal to 0. When s equals 0, f of 0 will be equal to 0 raised to the power 3. We are using this model equation, plus 2 into 0 minus 1. This will give us minus 1. Then let's take the second value, s is equal to 1. Now f of 1 will be equal to 1 raised to the power 3 plus 2 of 1 minus 1. 2 times 1 is 2 plus 1, 3. 3 minus 1 is 2. So you can see now we have achieved this. This is negative. So this is equal to negative and this is equal to positive. So they are opposite in signs. when we talk about the two values being opposite in signs, it means when one is positive, the second one will be negative. So now you can see we have to take note of this. We have two values, so that means a root lies between 0 and 1. So now we are going to choose, we are going to choose x naught to be equal to 0, the one with the negative. So anytime we are doing any replacement, anything that value that has to do with x naught will come from negative. Then our x1 will now be equal to 1. So anything that has to do with x1 is positive, anything that has to do with the x naught is negative. So we should have this at the back of our mind, just like the bisection method. This particular method of first position, using that formula, it closely relates or resembles the bisection method. So we have chosen our x naught to be the root lies between 0 and 1. So, and this 0 is what produces the negative. F of 0 is negative. Then this one, f of 1 is positive. So anything that has to do with x naught, f of 8 will be negative. Anything that has to do with x1, f of 8 will be positive for us to replace. Right now, let us go ahead to get our x2 using the formula for the method of first position. X2 will now be equal to x naught. What is our x naught? Is 0 minus. Now what is our f of x naught? Our f of x naught is f of 0, which is minus 1. Then x1 minus x naught, x1 is 1, minus x naught minus 0, then all over f of x1. What is our f of x1? Our f of x1 is 2, minus, the minus sign is there, then f of x naught is minus 1. So you put it there like that. So this will now be equal to, x2 will now be equal to 0, minus times minus is plus, plus 1 minus 0 is 1, 1 times 1 is 1, all over 2 minus minus 1, minus times minus is plus, it will now be 2 plus 1, that is 3. So 0 plus 1 over 3 will give us 0.3333. So we are working with 5 decimal places. So our x2 is that value that we have there. Now, for us to make progress, we are going to get what we call our f of x2. Our f of x2 will be equal to f of 0.33333. Anytime you talk about f of, we are using this model equation, this will be 0.33333, all raised to power 3, you can see it here, plus 2 into 0.33333 minus 1. Pressing your calculator, let's see what we are going to have. Note we are working with 2 decimal places. That value will be minus 0.29630, minus 0.29630, minus 0.29630. And again, if you look at it, of course this is equal to negative, so it has a negative sign, so it's equal to negative. So you can see that our f of x2 is negative. Note our x1, our x naught is 0, our x1 is 1. So it means since this is negative, this particular value will come and replace our x naught, because x naught, anything that has to do with negative has to do with the x naught. So this value will come and replace our x naught, this value here, x2 value. So we will now come and we're now going to get a new value for x naught, while our our x1 will be retained. Because this is negative, anything that has to do with negative, so our new x0 will be equal to 0.333333. We are working with 5 decimal places. Then our x1 will be retained. Our x1 remains 1. So it means now you can see why it is called the method of first position. It is only this one that will be changing. We've used it to get x2, but x0 and x1 will be fixed there in the formula. It's only this one that will be progressing. Now the next value we are going to get using this formula is x3. Everything there remains unchanged. Our x0 and x1 will be renewing it based on the sign. And when you talk about f of x0 will be negative, f of x1 will be positive. So that is what we must be maintaining all through the use of this particular formula. So we come here now for us to get our x3 now will now be equal to, what is our x0? Our new x0 is 0.33333 minus, then what is our f of x0? F of this, which is the value we got here, will now be bracket minus 0.29630. Then you now have your x1 is 1 minus your x0 minus 0.33333. Then all over our f of x1, which is f of 1, is 2. We got it before. Then minus, there is a minus sign there. Then of course f of x0, f of this value is minus 0.29630. So when you have that, our x3 will be equal to 0.33333 minus times minus, of course, will become plus. So that will become plus. Then by the time you carry that out, you are going to have, you subtract 1 from this, you are going to have 0. You will have this will now become positive. This will now be 0.29630. Then this minus this will now be equal to 1 minus 0.333 will be 0.66667. All over, you add minus times minus will be plus. 2 plus this will be 2.29630. So you have to multiply this. You multiply this and divide by this. Then you now have your x3 will now be equal to, permit me to clean this side. You now have your x3. Your x3 will now be equal to 0.33333 plus, you multiply that and divide by that, you are going plus 0.086 0.08602. So our x3, when you now add it together, will now be equal to 0.41935. 0.41935. So this is our x3. So you come again to get your f of x3. Our f of x3 will be equal to 0.41935 all raised to power 3. We are using the model equation, plus 2 into 0.41935 minus 1. When you press that in your calculator, your f of x3 will be equal to minus 0.08 minus 0.08756, and again this is equal to negative. Anytime we have negative, x0 is replaced. Anytime we have positive, x1 is replaced. Now since it is negative, our x0 will be replaced. This value for x3 will now replace our x0. Our new x0 will now be 0.41935. Then our x1 will be retained and it remains 1. So our x1 remains 1. Again, we are going to proceed to use the formula to get our x4. We are putting x3. Now we want to get our x4. Now we want to get our x4. So our x4 will be equal to, what is our x0? 0.41935. Then minus, what is our f of x0? F of that is minus 0.08756. Then all over f of x1. Of course, our f of x1 is 2 minus then f of x0 bracket minus 0.08756. Then of course here you put your x1 is 1 minus our x0 0.41935. So you put it there like that. Permit me to write it neatly. Let me write it neatly. Let me bring it down a bit. So our x4 will be equal to x0 is 0.41935 minus, then f of x0 is this, minus into 0.0808756. Then into x1 is 1 minus x0 is 0.41935. Then all over f of x1 of course is 2 from the beginning. There's a minus sign there. Then minus f of x0. F of x0 is minus 0.08756. So that is what you have there. So our x4 will be equal to, permit me to clean this one off. So our x4 will be equal to, it will now be equal to 0.41935, then plus, you take this away from this and multiply it by this, you are going to have 0.050842 to 5 decimal places, or 84 rather, then all over 2 into minus times minus is plus. This will be 2.08756. So our x4 will now be equal to, when you divide this, 0.41935 plus you divide this by that, you are going to have 0.024435. 0.02435. And when you add that, our x4 will now be 0.44370. That's our x4. Now again we have to check for our f of x4. So our f of x4 will now be equal to 0.44370 all root power 3. Anytime you see f of, we are using the model equation, plus 2 into this value 2 into x4, 0.44370 minus 1. Again, pressing your calculating aid, our f of x4 is minus 0.02525 minus 0.02525, and that is again negative. Now anytime we have a negative sign, x0 is replaced, x1 is retained. So now our new x0 will be equal to this value 0.44370. Our x1 is retained. Our x1 is 1, or you can call it 1.0. So our x1 is 1. So now we are going ahead to get our x5. Let's go ahead to get our x5 using this same formula. Getting our x5 is as simple as anything. So here, our x5 is equal to, now we have value for x0 and x1, so we will keep renewing x0, x1 depending on the sign. F of x0 and f of x1 must be opposite in sign, or must be of opposite signs. If f of x0 is negative, then f of x1 must be positive. Both of them are not permitted to have the same sign. So that's what gives us the condition to replace either x0 and retain x1. So now our x0 is 0.44370 minus, then of course our f of x0 is minus 0.02525. Then our x1, that is x1 minus, the x1 is 1 minus x0 is 0.44370 all over f of x1, of course, is 2. It has not changed, minus, then f of x0, or f of x0 is minus 0.02525. So when we come now, we are going to have our x5 to be equal to 0.44370 minus times minus, we turn to plus. So we have our positive sign there. So by the time we subtract this from 1 and multiply it by that, we are going to have 0.01405 all over 2 into minus minus will be 2.02525. So our x5 will be equal to 0.44370 plus, when you divide this, you are going to have 0.00694. 0.00694. x5 now becomes, when you add this to this, our x5 will now become 0.45064. 0.45064. So that will now become the value for our x5. Now we'll go ahead, we'll take a step further. If you look at, we have been able to achieve one level of decimal place accuracy, but that is not enough. 0.4. Now we are going to check for f of x5, and that will be equal to 0.45064 raised to power 3 here, plus 2 into that value, 0.45064 minus 1. Then our f of x5 will give us a negative number, is minus 0.00721. Minus 0.00721. And again, this is giving us a negative sign. So again, Anytime we have a negative sign, x0 is replaced. Anytime we have a positive sign, x1 is replaced. But since it's a negative sign that we have, we are going to replace our x0 with x5. So our x0 will be equal to 0.45064, while our x1 will remain 1. You see it? Our x1 will now remain 1. So we'll now go ahead to calculate our x6. We'll go ahead to calculate our x6. I told you from the beginning, please wait patiently to the end of this class. You will see how the results are compiled, and how interpretation is made. So our x6 will be equal to, what is our x0? 0.45064 minus into what is our f of x0? Our f of x0 is minus 0.00721. Then what is our x1? Our x1 is 1 minus, that is x1 minus x0. Our x0 is 0.45064. Then all over, our f of x1 remains 2 minus our f of x0 is minus 0.00721. You can see how simple this thing is. So our x6 will be equal to 0.45064. Minus times minus again will become plus. So you say 1 minus this, 1 minus 0.45064. Then you multiply it by minus 0.00721. You are going to have 0.00396 all over 2 minus minus will be 2 plus, so 2 plus that will be 2.00721. So when you divide this, you are going to have your x6 is equal to 0.45064 plus 0.00396 divided by 2.00721 is 0.00197. 0.00197. So when you add that, our x6 will become 0.45261. So you can see that x5 and x6 now at 2 decimal places, they are the same, 0.45, 0.45. So we'll take more iterations and see what we can achieve at the end of the day. So we have our x6 to be 0.45261. Now let us get our f of x6. It will be 0.45261 all raised to power 3. We are using the model equation to get anything. F of plus 2 into that value, 2 into x6, 0.45261 minus 1. Pressing our calculator, our f of x6 will be minus 0.00206, and again this is negative. You see it? Minus 0.00206. So if f of x6 is negative, then we are going to replace x0 again. Anytime we have a negative sign, x0 is replaced. So our x0 will now become 0.45261. Then our x1 is retained. Our x1 remains 1. Now we go again, take the next iterative step to get our x7. So we are coming here to get our x7. Please wait patiently to the end of this video. Subscribe to my YouTube channel, Dr. Chris Esekaibe. Click on the bell button for notifications. Share my video on your social media platform, your Facebook, your WhatsApp platforms, and other social media platforms. Like my videos, And as you do, God will bless you. So we want to take a step now to get our x7. So getting our x7 will now be, I told you it's only this that will be increasing. The formula there remains unchanged. So our x7, what's our x0? Our x0 is 0.45261 minus f of x0 is minus 0.00206. Then x1 is 1 minus x0 minus 0.45261 all over our f of x1 is 2 minus, then f of x0 is minus 0.00206. So our x7 will be equal to, take this away from 1, multiplying it by this, minus times minus is plus, so you have 0.45261 plus 0.00113. 0.00113 all over this. You now have 2.00206, because minus times minus again will give you plus. So you have that our x7 will be equal to 0.45261 plus, when you use this to divide that, you are going to have 0.00056. 0.00056. When you add that, our x7 will now be equal to 0.45317. 0.45317. So that will be our x7. Permit me to clean this part of the board. So you can see x6 and x7 are now equal at 2 decimal places, 0.45, 0.45. So we have been able to achieve accuracy up to 2 decimal places. Now let us get our f of x7, and that will be equal to 0.45317 all raised to power 3 plus 2 into 0.45317. We are using this model equation minus 1. All you need to do is to press your calculator. So f of x7 will be minus 0.00060, and this is equal to negative. So it is negative. So you can see that f of x7 is negative. Again, it means our x0 will be replaced. So our x0 will be equal to 0.45317. Our x1 will now be equal to 1. You can see how simple this can be. So permit me to get our x8. Then we'll now compare the level of accuracy with that of x7. Permit me to calculate our x8. So if you come here now, our x8 will be equal to, x0 is 0.45317 minus f of x0 is this, minus 0.00060, then into x1 is 1 minus x0, 0.45317 all over f of x1 remains 2. There's a minus sign there. Then f of x0, which is f of 0.45317, will now be minus 0.00060. So our x8 will now be equal to 0.45317 minus times minus is plus. 1 minus this multiplied by this, we are going to have 0.00033. 0.00033 all over minus minus will be plus 2 plus that will now be 2.00060. So our x8 will now be equal to, permit me to rub off this part of the board. So our x8 will now be equal to 0.45317 plus, when you divide that, you are going to have 0.00016. 0.00016. When you add that up, you have x8. Our x8 will now be equal to 0.45333. So that is our x8. So you can see that our x7 and x8 have the same values at 3 decimal places. 3 decimal places. So permit me to write out the summary of results so that we can make comparison. Now we have solved up to x8 and we have achieved 3 decimal places level of accuracy. Now I want to write out the results summarily, so which we call the summary of results. Until the results are explained, we have not achieved anything. So summary of results. So here our x0 is equal to 0, our x1 is equal to 1.00, our x2 is equal to 0.33333, our x3 is equal to 0.41935, our x4 is equal to 0.44370, our x5 is equal to 0.45064. Permit me to share the board. Then our x6 is equal to 0.45261, 0.45261. Our x7 is equal to 0.45317, 0.45317, and our x8 is equal to 0.45333. So you can see, but from this same problem we solved using the Newton-Raphson method, the real root is x is equal to 0.453, 0.45340, like that. So this is the real root. Now you can see that this method of first precision has been able to achieve accuracy up to 3 decimal places. Up to 3 decimal places, 0.453, 0.453 for x7 and for x8. So we have been able to achieve accuracy up to 3 decimal places. If you look at how we started, we chose x0 and x1. x0 is negative, f of x0 will be negative as retained, while f of x1 will be positive. Then from there we got our x2. You see they started converging from x3 at 1 decimal place, 0.4, 0.4, 0.45. Then from the 5th iteration between x5 and x is 0.45, 0.45, we're achieving 2 decimal places level of accuracy. Then again at x7 and at x8, we were able to achieve 3 decimal places level of accuracy, 0.453, 0.453. But the actual root from the solution we got using the Newton-Raphson method is 0.4534 at 5 decimal places. So you can see that even the method of first position has converged faster than the bisection method. The bisection method, we solved up to 10 iterations. At iteration 10, we could only achieve two decimal level of accuracy. We got 2 decimal places level of accuracy, 0.45, 0.5 at the 10th iteration using the bisection method. When we use the Newton-Raphson method at the 5th iteration, we got 5 decimal places level of accuracy. Now we have used the method of first position. You can see that at the 8th iteration, we have gotten 3 decimal places level of accuracy. That means for this particular problem, the Newton-Raphson method is the best for this method, followed by the method of first position, then followed by the bisection method. We cannot say because this method is the oldest or it's one of the oldest, we should just throw it away. No, we cannot throw it away because it is still very useful. You can see that despite the fact that it is old and despite the fact that it closely resembles the bisection method, it has produced a better result than the bisection method. The method of first position has gotten a better result. It has produced a better result more than the bisection method. But the Newton-Raphson method is best for finding a real root for any algebraic equation. So these 3 methods, we have looked at the bisection method, the Newton-Raphson method, and the method of first position. For this particular problem, the Newton-Raphson method is the best, followed by the method of first position before the bisection method. Though the method of first position is old, it has been able to achieve accuracy or better accuracy than the bisection method that it closely resembles because of the use of signs. Now, thank you once again for listening to my class today. God will bless you on every side. If you have any challenge in any topic in mathematics, please do well to put it in the comment section. You can contact me if you have any challenges in mathematics and statistical research. My area of specialization is numerical analysis. I said it in my last video. I hold a bachelor degree in statistics with a very good grade, a second class upper division. I hold a master's degree in mathematics and a PhD degree in mathematics. I specialize in numerical analysis, scientific computing, and data analysis and modeling, and also statistical analysis. You can contact me with your research work for assistance, and as you do, God will bless you. Please don't forget to subscribe to my YouTube channel, Dr. Chris Esekagbe. Click on the bell button, share my videos on your social media platform, like my videos, and as you do, God will bless you. I'll be bringing us another topic again in our next class, and we shall be looking at numerical differentiation. Numerical differentiation. There is a formula for numerical differentiation, and that formula is gotten using the Newton's forward interpolation formula. We use the Newton's forward interpolation formula, the Newton's backward interpolation formula for numerical differentiation. How the formula will derive, we'll use it, we'll see how we can implement the formula in carrying out differentiation. Then we'll do our differentiation using the conventional method we know, and we compare the results. Of course, the difference between the two results, the result from the approximate method and the result from the conventional method, is what we call the truncation error in numerical analysis. So we'll be doing this in our next video. Please expect to see it. It will come up, and as you do, God will bless you. Once again, enjoy the rest of the day. God bless you. Bye.